So now we're going to go over our in-class exercise here on SN1 and SN2. But before we go into that, I want to stress further something that we talked about in Organic 1. And that's that these in-class exercises are just a few practice problems on each topic. And if you want to be successful in this course, you need to do as many practice problems as possible. And so you need to do these, do the homework problems, do some of the old exams, do some of the problems at the end of the chapter. But the more practice problems you're able to do, the better off you're going to be. So when we approach one of these questions on SN1, SN2, the first thing we want to do is look at the reaction conditions and determine, are these conditions for SN1 or SN2? So in this first example, we have water as the solvent. Now water is a polar protic solvent, so that tells us that these are SN1 conditions. Now our leaving group, we may notice, is primary. And we know that primary is not very good for SN1. But this primary carbocation that would form after the bromine leaves is a benzylic carbocation. It's adjacent to the aromatic ring. And we said those are actually fairly stable. And so our nucleophile then, the hydroxide, can add to that and give us our SN1 product here. Now I'm going to identify each of these as SN1 or SN2. And there are times where you might not think that that's important, because the product of this reaction would have been the same whether it was an SN1 or SN2. But it does matter, because in certain cases, such as Part B we have a primary leaving group again. But our solvent, DMSO, is an aprotic solvent, and one that favors SN2. The reason that I say this is important, if this was an SN1 reaction, so if we found ethanol as our solvent here, this reaction is not going to work. And if this reaction doesn't work, then we're done. We don't have to figure out what the product is, because there isn't one. But because we have an aprotic solvent, we know this is SN2, and we know that our nucleophile, the nitrile, or the cyano group, will replace the iodine. In C, we have a leaving group that's tertiary, and we have methanol, which is protic. So these are good conditions for an SN1 reaction. And so as a result here, our leaving group, the bromine, will get replaced by the nucleophile, the methoxy group. In Part D, we have acetone, which is aprotic. That means we're looking at SN2 conditions. We have a secondary leaving group, and with the tosylate we have a very good leaving group. So we will get replacement of the tosylate with the iodine. And finally, in this group Part E, we have a protic solvent, ethanol, looking at SN1. Again, we have a primary carbocation, but this is our allylic cation. It's adjacent to an alkene, so the alkene stabilizes the cation. and that means we can get the substitution to take place. Alright, question 2, we have a reaction that probably doesn't, at least initially, look like a nucleophilic substitution. But there must be something here that relates to substitution, or else I wouldn't have put it in this situation. And this sort of brings us to a situation that we run into in organic chemistry. So here's a reaction that maybe didn't do what we expected it to do. We know that bromine adds to an alkene, and the alkene converts to an alkane, and we end up with halogens on both carbons of the alkene. But clearly that's not the product that we got here. And so we need, in this situation, to use what we know about the mechanism of this reaction, and maybe others, to figure out what happened. So I'm going to start this the way we think it should start. The alkene attacks the bromine, and we end up with our three-membered ring, the bromonium ion. And this is where, if bromide attacked and opened up that ring, we would end up here. But if you think back to when we learned this reaction, we saw some examples where if we had other nucleophiles present, such as water could add in preferentially. Well, this molecule has an alcohol in it. So could that alcohol play the same role as the water did and add in to the bromonium ion instead? And the answer is yes. Now, which carbon will it add to? Well, we've seen before it'll generally add to the more substituted carbon because of the positive charge. So the alcohol attacks, and that's what triggers opening of the three-membered ring. Now we can probably see that this is going to form a ring. We just might not be able to see here yet what the ring is going to look like. So one of the things I often suggest doing in these kinds of situations, it helps us to see what this is going to look like, is let's redraw this compound exactly the way that it was. Then what I'm going to do is, it's going to look funny, but I'm just going to draw the new bond in. So there's the new bond that formed, the carbon-oxygen bond. And I'm going to delete the bond that was broken, the carbon-bromine bond. Now that still probably looks kind of funny. So now I'm going to number the carbons in that ring. And you'll see why I do that in a moment. These numbers are going to help us for the purposes of mapping. And what you can see is we have a six-membered ring. So now I'm going to draw a six-membered ring in the way that we normally would. And then I'm going to put these numbers back in so that we know what goes where. So we can see on the first carbon we have a carbon bonded to a bromine. 2, 3, 4, and 5 just have hydrogens, and then oxygen has is a cation as well. And so by doing that, we can now see that the only difference between that structure that we have now in our product is that we have to lose a hydrogen. And that's it. All right, in question 3, we're trying to rank compounds on their ability to undergo SN1 reactions. And really, this is another way of asking which one of these is going to make the most stable carbocation, because the more stable the carbocation is, the more likely it is to undergo SN1. And so you'll notice up here at the top left, we have an iodine that when it leaves, that carbocation is resonance stabilized by 1, 2, 3 alkenes. That's going to be better than the one that's stabilized by only 2 alkenes. And that'll be better than the ones that are stabilized by only 1 alkene, which are these two at the bottom. We can rank these two because iodine is a better leaving group than chlorine. Otherwise, those two molecules are the same. And then finally, this one, which would have the leaving group on an sp2 carbon, we've already talked about those generally don't form at all, and so this one's not going to work. All right, our final question here is actually a fairly difficult one. So we've said that in an SN2 reaction, we get inversion of configuration, and that in an SN1 reaction, we get generally racemization. But this reaction is giving us retention of stereochemistry. So you can see here, this chlorine has been replaced by a hydroxide, but the stereochemistry hasn't changed at all. So how does that happen? Because for retention to take place in a single step, we'd have to have the nucleophile come in from the exact same spot where the leaving group is. And that generally doesn't happen because the leaving group is blocking that position. So we have to start thinking about other things that could happen. And so sodium hydroxide here, not only is it a nucleophile, but it's also a base. And if it's a base, are there any acidic hydrogens? Well, that alcohol hydrogen could be acidic. And we form an anion. That anion could then kick out the chlorine. And if you think about how that reaction occurs, that's going to happen from the opposite face. So here we've had an inversion. But now that three-membered ring can open back up if we get a nucleophile to attack it. And so when that happens, we have a second inversion. And then just to complete the mechanism, this picks up a proton from water to get to the product. But what's happening here and what gives us the retention of stereochemistry is that we had not one inversion of stereochemistry, but 2 inversions of stereochemistry. And if you invert the stereochemistry twice, it's going to look like it's been retained.